All right, so at this point, we have learned about three sorting algorithms. So these are methods that take in an unsorted or a random array and it puts them in increasing order, in sorted order. So the bubble sort we found was the slowest, and here's a peek at the bubble sort one more time. Okay, so this bubble sort, you'll notice that we have a loop inside of a loop. So we have a nested looping structure. So in terms of efficiency, when we're talking about how fast an algorithm is, what we're looking for are how many comparisons are made. So something like this is a comparison. Yes, there are other things that take time, like swapping the elements actually takes some time. Checking these loop conditions takes some time as well. But generally this will take the most amount of time, is comparing one value to another value. So we want to talk about on average how many comparisons, like how many times will this line of code, will this Boolean condition, how many times will this condition be tested? So in terms of bubble sort, we say that the efficiency is n squared, where n is the size of the array. Okay, so n is the size of the array, or the length of the array. So if the size of the array, let's just say, for example, is 100, okay, then the bubble sort is going to make 100 squared, 100 times 100. So that's going to be 10,000 comparisons. Selection sort, if you look at that code, you might be fooled into thinking, oh, it's there's only one loop for selection sort. And even though we only see one loop here, remember that findmin has a loop within itself. So if you go and look at findmin, you'll notice here is a comparison here, and that is inside a for loop unto itself. So selection sort does have a loop inside of a loop, just like the bubble sort did. So the time complexity for this is also n squared. You may, if you've done some research in terms of efficiency of algorithms, you may have come across this function notation. So those studying grade 11 and 12 math, you may have studied function notation like f of x or g of x. Well, in terms of efficiency in computer science, we call it big O of n. So instead of f or g, we use capital O for efficiency, and n is the size of the array in this case. So we would say that bubble sort is O n squared, and selection sort is also O of n squared. That's the efficiency. So selection sort would also take 10,000. Now, going back to bubble sort, you might say, well, hold on, bubble sort is going to be a little bit faster than n squared because every pass we make through the array, we're going one less each time, so it's accelerating. And that is true, but on average, we basically say that this is going to take n squared. So it is actually a little bit less than that, but in terms of efficiency, we just say that it's n squared efficiency. Now, merge sort. Merge sort is a recursive sorting algorithm. It is quite fast, and the efficiency is, we say, n log n. N times the log of n. Some people put parentheses here, just showing that this is a function. Okay, so what in the world is the log of n? Oh, and I should say that that's base 2. So some of you have studied logarithms, and if you haven't, it's really just an exponent. So if I ask you, just in a nutshell, here's a little tutorial on logarithms. If I say 2 to the what is equal to 16, let's call that x instead of a question mark. So, well, we all know that x would be 4 in this case. Okay, that would be the answer. What if I said 2 to the x equals 32? Well, x would be 5. What if I said 2 to the x equals 1? So in that case, x would be 0, if you remember your exponent rules. What if I said 2 to the x equals, let's say, 100? Well, it turns out there's no exact value for x. So we know that 2 to the power of 7 is 128, and 2 to the power of 6 is 64. So we would argue that this answer here, this answer for x, would be in between 6 and 7. Now, how do you get the decimal answer? Well, you use logarithms. So with your calculator, you would just do the log of 100 base 2. Okay, and that would get you the answer. So yeah, so the answer is going to be somewhere in between 6 and 7. So over here, if I look at the merge sort, if I had an array of size 100, bubble sort would make 10,000 comparisons, selection sort 10,000 comparisons, but merge sort would take n times log of n base 2. So this is going to be 100 times the log of 100 base 2. So this is going to be 100 times. Now, what's the log of 100 base 2? We said it's going to be in between 6 and 7, but for this case, we'll just put 7. So that will ensure that will give us a number that's higher than 100. So 2 to the power of 7 is equal to 128. So that definitely covers 100. So instead of putting a decimal here, we just put the highest integer. So that would be 7. So that's going to be 700. So only 700 comparisons for merge sort, whereas selection sort is 10,000 and bubble sort is 10,000. So we're talking about major efficiency here, and this difference only gets more significant with larger arrays. So if we had an array of size 1,000,000, then we are looking at a lot smaller number for merge sort. Okay, so this is just a little note on comparing sorts, but we are now going to move on to another search algorithm called binary search. So if you remember, we had a method called linear search, which hopefully you all understood. It's one of those kind of easier methods. It just has one loop, and this method accepts an array of ints. Oh, and by the way, this array does not have to be sorted. It could be random, and it accepts a key. And basically, we're just going to look for key. We're going to see if we can find key inside this array. And if I find it, we're going to return the index at which it's found. But if we don't find it, we're going to return -1. Okay, so this is a pretty classic standard search algorithm. We just basically go one at a time, looking through the array, looking for our key, and when we find it, we stop the loop, and if we don't find it, then we're going to return -1. Now, question. And by the way, this method does not change the array. It does not make any swaps. It does not physically move array elements. It's just looking for the key. So be aware of that. A search method does not change the array like a sort method does. So the question is there a faster way to search through this array for a key? And the answer is yes, but you have to sort the array first in order to find a key faster. And let's dive into this and just talk about this. Okay, so here you have a 20 element sorted array. So this element has been sorted. We've taken the time to sort the array using, let's say, merge sort. Now, let's say I'm looking for the number, 62. Okay, so we as humans can look at this and see, oh yeah, there is a 62, and that occurs at index 17. But if you're programming a computer, you need to give it instructions. You need to tell it, how to find that 62. So right now we have a method called linear search that basically starts at the beginning, and it says, is that it? And then it goes to the next one. Is that it? Is that it? Is that it? It basically goes one at a time until we get to 62, and then it returns 17. Now, this would not take too long if it's a small array, but if this array had 1,000,000 elements in it, that could take a long, long time. It could take 1,000,000 comparisons if it finds it at the very end. So how can we speed this up if the array is sorted? Well, we can use something called the binary search. Okay, and binary search takes a little more code than the linear search, and remember that the array must be sorted in order for this to work. So that is key. Okay, so how does this work? Well, we basically, binary search, you'll be happy to know, does not involve recursion. That makes it a little bit easier to understand and to code. But basically what we do is we create three variables: low, and that's going to be 0, so the starting index. High is going to be the highest index. And then we calculate the middle. So that's just going to be the average of low and high. So in this case, that is going to be 9.5. But we're not going to have a decimal. So we're just going to cut off the decimal and just make that our mid. So you're going to create three variables: low, high, and mid. And you're going to assign low to 0. And you're going to assign high to the last index, and then mid is going to be halfway between low and high. Okay, so basically, you're going to look at the middle position, and you're going to ask, is that my key? Is that what I'm looking for? Okay, once again, let's pretend our key is 62. So let's say we're looking for 62. So we first look at the middle element and we ask, is that it? And if it is, if we got lucky and found it, then we return mid. We return 9, and that would be the location of our key. But if since this value is less than our key, what we're going to do is we're going to move low up to mid plus 1, and then we're going to recalculate mid. We're going to recalculate mid. Again, that's going to be the average of low and high. So low plus high divided by 2. So that is going to be 29 divided by 2 is going to be 14, because we're going to cut off the decimal. Okay, and then we ask again, is that our value? You know what? I'm just thinking, I'm going to change my key just for the purpose of this demonstration. Let's change the key to, let's say, 40. Okay, so let's say we're looking for the number 40. All right, so basically we ask, is this the key at mid? And the answer is no. So this time, this value, this element, is larger than our key. So this time we're going to move high down to mid minus 1. And then recalculate mid. Okay, so mid is going to be the average of low and high. So we just add up low and high and divide by 2. So that's going to be 23 divided by 2. So that's going to be 11.5. So I will just call it 11. And then we ask, is that our key? 35. Is that our key? No, it's not. Is it less than our key? Yes, it is. So we're going to move low up. Okay, low is going to be equal to mid plus 1. And then we recalculate mid. So mid is going to be the average of low and high. So in this case, the average is going to be 25 divided by 2, which is going to be 12.5. So it's going to be there. Okay, and then we ask, is that our key? So we look at the element at mid. So is 36, is that equal to our key? No, it's less than our key. So we're going to move low again. We're going to move low up to mid plus 1. And then we recalculate mid. And mid is going to be at the same, they're all going to be pointing at the same point this time. So now this is our last check. So is 40, is that equal to our key? Yes, it is. So we're going to return mid. We're going to return 13. Now, what if it wasn't? Like, what if our key was 41? Well, what would happen then is you would say, well, okay, 40 is less than 41. So you would end up moving low up to mid plus 1, like you always do. And then the moment the moment that low and high have crossed each other, so the moment that low becomes greater than high, we now stop and we return -1. So that's what tells you the binary search is finished and it hasn't found our value. Now that seems like it seems like a long algorithm when it's presented like this, but it actually finds your key so much faster, especially if this was a large array with 1,000,000 elements, because at each step you're eliminating half of the array. So each time you recalculate mid, you're eliminating half of the array each time. So you're kind of narrowing in on the key a lot faster. So I'm going to stop here, and I'm going to try and get you to code the binary search method on your own. Put it in your array methods class, and see if you can finish it. And then I'd also like you to think about the efficiency. So how much faster is binary search than linear search? Oh, and before I let you go, you may be thinking, should we really use binary search? Because you actually have to sort the array first. You might think, couldn't we just leave the array unsorted and then just use linear search? Well, it depends how many times you're searching through that data, and in a lot of cases in the real world, arrays are being searched through many times per day. So it's worth it to sort the array once and then just keep using binary search over and over and over again. And then that would be a lot faster in the long run than just using linear search on an unsorted array over and over again. So it all depends on if you're going to be searching multiple times, then it's definitely worth it to sort and use binary search. Okay, that's it. I'll let you try and do the binary search on your own. Okay, thanks for watching.